those who are very young students don't know enough about societies. So the main goal of these societies is to work for the advancement of our disciplines and as well as applications, and in principle also to collaborate for any kind of human activity which can benefit from it. So the societies, they sponsor high-level journals, as you know. The Bernoulli Society in particular sponsors journals by itself in collaboration with the IMS and other societies, and in collaboration with commercial publishers as well. So the two main journals of the Bernoulli Society are the Bernoulli Journal, which is owned by the society, and the Stochastic Process and Their Applications with Elsevier. And another important activity of societies is to organize international meetings. And you also receive the flyer of the SPA conference, which happens every year, except when there is the World Congress, which is every 4 years. The main capital of these societies is the membership. It's not money. And so you might think, why to join societies? No? There are some advantages which you may consider as material advantage. Like if you go to a meeting, you get a reduced fee for your inscription, or you get free access to the journals. There are all these somehow material advantages. But you also have one big advantage, which is it's a very nice way to make scientific friends all over the world, because societies have people from, say, the Bernoulli Society has members. Let me keep from over 70 countries. And also what the society can do will depend very much on the renewal. Well, that means we need young people to join. So take your time over the weekend, think about this. And I have also applications, because as it's announced on the flyer, PhD students don't pay membership. So for students who want to join, I will leave these application forms on the desk of the secretaries, so you can fill in and give to me or to Bernardo Lima, who is there. Please, if you don't find me next days here, but I hope find. So thank you very much, and thank you.
Okay, so can you hear me? Yeah. So this is the fourth course of the first week about SLE, but we still don't know what SLE is. So the goal today is to define SLE. And that's essentially all we'll have time to do about SLE. We won't reach any of the properties or anything like that. That will be for next week after the weekend. So before I do that, I have two things to do. I will come back to what I told you yesterday, and then I will speak about the caudal case of Löwenchain. So recall what we did yesterday. So we started from the unit disk with a mark point at 0 and one mark point at 1. And we started with a red curve in this disk starting at 1 and going inside the domain. And we applied a few steps of a construction to encode this curve by a driving process. So I will just rewrite everything in order, just because that's very parallel to what I will speak about today. So this is a curve gamma, which is indexed by t. And so the order in which we did the things is first assume that, well, yeah, maybe, okay. So this was this map GT that mapped this back to the unit disk, and it was normalized to fix 0 with positive derivative. So the first thing to do was to parameterize the curve in a natural way, and this was done by assuming that GT prime of 0 was equal to exponential of t. So that took care of the parameterization of the curve, and it was essentially the way to forget the information we didn't care about the curve. We just want the shape, but not the exact speed at which the curve is described. Okay, and then we wrote Loeffner's equation, which was that the time derivative of gt of z was equal to gt of z times e to the I beta t plus gt of z divided by e to the I beta t minus gt of z. By the way, if you look at the notes, this equation is written in the notes, but the sign is wrong. In the notes, there is a minus sign. Well, this is swapped. And if you swap it, you don't get something very interesting, because that's the backwards flow I was using yesterday to prove the bijectivity of GT. If you put the minus sign, you go in this direction, and you map the disk to the disk minus a curve. So it contains more or less the same information, but not in the right way that we want to use it. So this is the right one. And the way to check is it should be asymptotic to gt of z at the origin. So when gt of z is 0, this is 1, and then you find that the derivative is equal to g. So that's how you come up with the gt prime of 0 equal to exponential of t. You just differentiate this at 0, and you find that it's a linear equation. And so the derivative at 0 grows like exponential of t. Okay, and then this beta t was what I called the driving function. And it's a function that goes from r plus to r, and it's a continuous function. So that was the construction I explained yesterday. You start with a curve, and you come out with this driving function. And this driving function contains all the information about the curve. So if beta t increases, it tells you to turn to the right. Essentially, if beta t decreases, you turn to the left. If it's fixed, you go straight towards 0 along a green line. Or you can make a few pictures like this. And it really tells you that you look at the local behavior of the curve in a time parameter which is given by this. Okay. So what I want to do today is to tell you what happens if you look at the caudal case. So I drew the picture yesterday, but I didn't say anything about it, and I will come back to it. And that will be an occasion to prove actually something that looks like this in the caudal case. So yesterday I used this equation as a black box. I didn't tell you where it was coming from, except by saying that there should be a vector field doing such and such at different points. Now we'll get exactly a proof that this is true, except, of course, in the caudal case, the shape of the equation here will be different. But the idea is the same, that there will be some differential equation. Okay, so that's the second paragraph in this chapter, which will be caudal Loeffner chains. So just to recapitulate what we have, this was adapted to studying, for instance, the loop erase random walk from 0 to the boundary, because the topology was really a curve joining a point on the boundary to a point inside the domain. Now the idea you should have in mind is that of the exploration process of percolation. So just to remind you what this process is, you start with the triangular lattice on the upper half plane. Like this, you look at side percolation on this guy. will be terrible, but okay, this is the triangular lattice. And you call every vertex white or red with probability 1/2, except that on the boundary, all the points on the right are white and all the points on the left are red. And then you explore the boundary between these clusters. So this is the kind of curve you have. And we want to do something similar in this setup as we did for the loop-reduced random walk. So we want to describe the possible scaling limits in terms of conformal maps. So if you were really listening yesterday and if you listen today, you will find lots of similarities because most of what I will say in the beginning will be very parallel to what I said, except some things are a little bit clearer in the radial case. For instance, the fact that this was bigger than 1, so the fact that the time parameter was well defined, that was clear in the radial case by the Schwarz lemma, and this was not completely clear. In the caudal case, you'll see that the situation is reversed. The choice of the time parameter is not completely obvious, but the equation is clearer than in the radial case. Okay, so the setup is the same, but I will write it anyway. So we are given curve gamma t, t positive, which is continuous, such that so gamma 0 is equal to 0. Gamma t is in the open upper half plane H if t is positive. And I'm assuming that there is no double point, so gamma t is different from gamma s if t is different from s. And I'm also assuming that gamma goes to infinity. So gamma t goes to infinity as t goes to infinity. That's the same assumption as assuming that gamma went to 0 in the case of radial SLE. You just want the curve not to spend too much time in its own neighborhood, because that would make the thing pathological. So this is what we have, and so we'll live in H, and we'll do the same as yesterday. So we'll define HT, well, we'll define KT, which is the path up to time t, and we'll define H sub t, which is the upper half plane minus KT. So I'll keep repeating myself. This is H, this is 0, and you have a curve here. And let's say this is the curve at time t. So if I want to do something that is very parallel to yesterday, what I want to do is to look at HT, which is the complement here. And I want to encode the shape of HT as a conformal map. So the same as this GT, and it will have the same name. So I will define GT, mapping HT conformally back to the upper half plane. So back to the conformal, to the upper half plane here. Okay, again, GT exists by the Riemann mapping theorem. HT is a simply connected domain. It's not equal to C, and it's related to H by a 3-parameter family of conformal maps. So as before, we need to normalize G in some way. And so if you remember, there was this point here, which was somehow the target of the curve. So the curve is going towards 0, and this was the fixed point in the evolution here. So here we want to do the same. We want GT to fix infinity. So we want GT of infinity to be equal to infinity, which is the same as saying that GT of Z goes to infinity as Z goes to infinity. So we want the map to be, well, to fix infinity and to be somehow local, and to say something about what happens in the neighborhood of gamma. Okay, if you remember your complex analysis classes, you know that there is something called the Schwarz reflection lemma, saying that if you fix a point on the boundary of a flat surface, then you can extend the map by symmetry, and locally it behaves like a conformal map. So if you look at G of Z bar, which is G of Z bar, it extends the map across a flat boundary. And infinity is on such a flat boundary. It's on the real line, actually. So what it tells you is that the map can extend across infinity back and be conformal. So what it tells you is something about the expansion of G around infinity. Okay, if you have not had complex analysis classes, just use what I will say as a black box. And say essentially it will tell you that if you take a map from HT to H, which goes to infinity at infinity, the only possible expansion at infinity will be that GT of Z at infinity will be asymptotic to Z, to lambda Z. The only possible behavior on the neighborhood of a flat surface is just a scaling. And then there will be additional terms of lower order, so A0 plus A1 over Z plus other terms. So this is the expansion of G at infinity. And fixing infinity, that's fixing one real parameter is the image of a boundary point. So we still need to fix two real parameters. And by the Schwarz reflection lemma, all these parameters are real. So we can fix two of them. First one will be lambda. We'll assume that G is as close to identity at infinity as possible. So that's what we want to do. So we'll assume that lambda is equal to 1. And this is like a translation term at infinity. So it plays the role as the argument of G prime in the radial case. And so we want it to be 0 because that's what will be closest to identity. So we want A0 to be equal to 0. So in other words, what we have as a normalization will be that GT of Z is equal to Z plus, and then the rest is completely determined by the shape of gamma. Once you fix these 3 degrees of freedom, everything else is fixed for you. In particular, this parameter A1 here is fixed by gamma. And I want to call it A of KT of Z plus big O of 1 over Z squared. So this is the normalization for G in the chordal case. So let me finish the drawing here. As before, what you have is a map from the complement of the curve to H. It will extend to the boundary, but with the usual thing that two boundary points of the curve that are on different sides of the curve are actually considered as two different boundary points. So the technical term that you want to look for, if you want to look in the book, is prime end. But morally, just say that the curve has two sides, and these two sides are different boundary points. And so what GT does is the same as yesterday. It opens up the curve, and then it flattens everything to R. And so it maps the picture like this. So this is the image of gamma. And the tip here, which is gamma t, will be mapped by GT to something here. And to follow the same notation as yesterday, this will be GT of gamma t, and I will call it beta t. And you will see that the role of beta t is very similar to what we had here. So it will play the same role as bt. It will be the driving function of the Leutner chain. All right, so the next step was to fix the time parameterization of the curve. And here, what we did was measuring the size of gamma t by saying that we wanted the conformal radius here to be like exponential of minus t. So here the conformal radius is just 1 over g prime. So we wanted to encode at which speed gamma approached 0. Here gamma approaches infinity, so it's still infinity distant from infinity for all finite time, so we need something else. We need to really measure the size of gamma. And as it turns out, the right measure for the size of gamma will be this parameter A of kt. So morally A of kt is the size of kt. And the term that is used now is the conformal capacity. of kt. So we want to use this to build some kind of time parameter. So here's the guess. Let's say that we continue gamma forward to gamma t plus s. Then if you map it by gt, okay, that was not a good idea to put this here. Beta t is gt of gamma t. So the future of the curve is here. And as before, we can map h minus the image of the future here. So this is gt of gamma between t and t plus s. We can map the complement of this back to the upper half plane by this map that I called gt and t plus s yesterday. So back to h. This will be normalized the same way. So with this expansion at infinity, z plus something over z. And then this map here, which is the composition of the two, you want to say that it will look like gt plus s. So you want this to be the composition of this and then this. And so you want to see, for instance, if the composition of this guy and this guy has the right expansion at infinity. So just compute. If you look at z plus a over z plus something, and you compose it with z plus b over z plus something, well, you just replace z by this on the left. So what you find is z is replaced by z plus b over z plus big O of 1 over z squared. And then a over z will be something like a over z times 1 plus b over z squared plus something, plus other terms. And then you see that this contributes to the term in 1 over z as a over z, and the rest is higher order. So what you get is that this is z plus a plus b over z plus higher order terms. So what was multiplicative here at 0 here becomes additive. So that tells you that a is already behaving like a time parameter. Like a for this guy here will be the sum of a here plus a here. And so you want to use a as the time parameter. Well, a is additive, but it's not sufficient to be additive to be a time parameter. You need to be increasing. So here's the lemma. This a of kt, as t is positive, this is increasing. Okay, and then I put in brackets, because this is wrong, but morally you should think of it as true, that a of kt increases to plus infinity as t goes to plus infinity. So what is in brackets is not always true. I mean, it's true in many cases, but this is not sufficient to ensure it. And I will come back to it after I prove the lemma. So here's the proof. So first of all, we have this chain rule here saying that if you compose two maps, then A is additive. So if you want to prove that A at time t plus s is bigger than A at time t, all you need to show is that this term B here, which is the coefficient here, is positive. And A here will be what happens when you remove something. So what it means is that it's really sufficient to prove that A of kt is positive. So it's enough to prove that A of kt is positive as soon as t is positive. So of course for t equal to 0, you remove nothing, so G is the identity, and A of the empty set is 0. But what we want to show is that if what you remove is non-empty, so if you really remove something, then this coefficient is positive. Okay, so there are several ways to do that, but there is one way which is very nice and which will make you use the conformal invariance of Brownian motion. So that's good practice. So I will redraw something, and I will put it in a slightly more general setup. So let K be a compact set that touches the boundary and whose complement in the upper half plane is simply connected. So if you don't want to do it in generality, you should use K sub T as K, but it's true for any compact set. Okay, and then for this K, there is this map, G sub K, with the expansion Z plus A of K over Z plus something. That maps H minus K to the upper half plane H. Okay, what we want to show is that A of K is positive, and what I will claim is this, so the claim is that in fact there is a nice representation of A of K in terms of planar Brownian motion. So what can you do? And I will show you how to prove it. So this is the origin. I'm putting the origin inside K, but that's not really relevant. So pick little y positive, very large, and look at point IY in the imaginary axis. And then start from IY, start a Brownian motion, a planar Brownian motion, until it exits H minus K. So I take y positive, and I look at BT, which is a Brownian motion in the plane, starting from y, from IY. And I look at tau, which is the exit time of H minus K. So I wait for the Brownian motion to exit this. And it can exit in two different ways. It can exit either through the real line or through K. So let's say it exits through K. So this is what happens at time tau. Okay, what you can look at now is this. You look at the expectation starting from IY of the imaginary part of the Brownian motion B at time tau. So you wait for the Brownian motion to exit and to touch the boundary here. And whenever it touches, you measure the imaginary part. So in the case of Leibniz chains here, what you have is that this is positive if and only if you touch on K, and it's 0 if and only if you touch away from K. But that's not always the case. It's not the case, for instance, if K has two connected components, or if K is following the real line or something like that. So just look at the expected value of this. Okay, what is the order of magnitude of this? Well, essentially you can rescale the picture and say that y is 1 and K is very small. The probability that you touch K at all will be something like 1 over y, because that's harmonic measure from a fixed point on the line is proportional to the angle here, and the angle is proportional to 1 over y. So the probability that you touch K is like 1 over y, and if you touch K, then the typical imaginary part is of order 1. So you expect this to be of order 1 over y, and so you renormalize it by multiplying by y. So this is order 1. And as it turns out, as y goes to infinity, so this is order 1, but it converges to A of K. So So in particular, a of k is order 1. A of k is positive. This is bounded below by a constant, just by the argument I just told you, that you touch with probability 1 over y, and if you touch, you are above, say, epsilon with positive probability, conditionally that you touch k. So what you get is that a of k is positive from this representation result. So this is the claim. The claim is that you can represent this coefficient in 1 over z in terms of Brennan motion in the plane. So that might not be the shortest proof that the coefficient a is positive, but that's the shortest proof if you are a probabilist and if you already know about Brennan motion. Okay, apparently I need to keep talking while I erase the board, so I do that. So what's the idea? We know that Brennan motion is conformally invariant. I told you that during the lecture you saw this, or you will see that in the afternoon in the TA session. So we want to use that somehow. So we have a Brennan motion. The Brennan motion is just B. It starts at IY. It stops on the boundary of the domain. We have a conformal map, which is G sub k. So we know that the image of B by G will be something like Brennan motion. It will be time changed, but the exit points will be the same. And if you look at the formula, only the exit point is relevant. The time at which you hit is not relevant. So only B sub tau is appearing, and tau itself can disappear. So this is good news. We are in a nice setup that we can use the conformal invariance of Brennan motion. So the problem is, this map G is not bounded. Map G goes to infinity at infinity, and if you want to use something like the stopping theorem for martingale, then you're not happy with unbounded functions. You would like something to be bounded. So what is conformal, bounded, and related to the picture? Well, if you look at the expansion of G, which is here, well, you'll notice that G is bounded in the neighborhood of 0. It's only at infinity that is going big. And it's exploding like Z. So what we'll look at is just G minus Z. So we'll define HK of Z to be GK of Z minus Z. So now HK. So HK is not quite conformal because it's not one-to-one anymore because you subtract this factor Z here, but it's still holomorphic as a difference of two holomorphic functions. And that's enough to preserve the fact that Brennan motion is Brennan motion with a time change. Holomorphicity is enough. But this does not follow from the proof I told you 2 days ago, but it does follow from what Hugo will tell you this afternoon. So what you have is that HK of BT is a time-changed Brennan motion. In particular, it's a martingale. And this is where we really use the fact that the map is bounded. It would be a local martingale anyway, but it's a martingale because it's bounded by the supremum of HK. So this is bounded. So we want to look at imaginary part of things. So we'll look at the imaginary part of HK of BT. So what is it? It's the imaginary part of GK of BT minus BT. And let's say I call that YT. So that's a nice process, and YT is the imaginary part of a martingale, so it's a martingale. It's a martingale, so it satisfies the stopping theorem. So what we have is that Y0 is the expected value of Y at time tau. So I start from little y, and I have this equality by the stopping theorem for martingale. Okay, so now all I have to do is to look at this term and that term and see if I can compute them. So first look at y0. So y0 is the imaginary part of gk of the initial point minus the initial point. Well, that's the imaginary part of gk of iy minus iy. So what do I know? I know that gk behaves like z plus a over z plus something of higher order. So I can plug that inside. I know that y will go to infinity, so this expansion is relevant here. And so this is equal to, so iy plus a over iy plus big O of 1 over y squared. So that's the term for gk of iy minus iy. Okay? So as you see, the iy will vanish from this and that. And there is an imaginary part in front of that. And the imaginary part of 1 over I is minus 1. So this is like minus a over y plus big O of 1 over y squared. So that just comes from the normalization of g at infinity. Now what is y tau? Well, that's the imaginary part of gk of b tau minus beta. Okay, one of these terms, imaginary part of this and imaginary part of this, is easier to compute than the other one. If you look at the map, it maps the complement of k to the upper half plane, and this is b tau here. So if you look at the image of b tau by gk, it's somewhere here. This is gk of b tau. So it is always in the real line, because that's the image of the boundary, and you start with the boundary point. So what you get is that this is real. And so imaginary part of this is 0. So the expectation of y tau, which is the expectation of this, is just minus the expectation starting from iy of the imaginary part of b tau. Okay, so what we have is that this is equal to this, and now you multiply by y, you put a minus sign, and you let y go to infinity, and you find that y times this does converge to a. So that's what I was claiming, that this concludes the proof that a is positive. So is the limit as y goes to infinity of y expected of imaginary parts of b tau. Okay, so now we're almost done for the time parameterization of the curve. We have an increasing feature of kt, which is the coefficient in 1 over z here. And it's additive. So it's a nice candidate, and we want to use a of kt as time. So there is one thing that will be a little bit surprising. We will not use a as time, but we will not impose that a of kt is equal to t. And the reason for that is something that will come up next week. It turns out that we want the radial and caudal pictures to be as close to each other as possible. And in particular, we want that if you take the same driving process for both, you see very similar pictures. And the reason will be that if you want to measure, to describe something that is microscopic, well, it doesn't matter if it's going to 0 or to infinity. You really want to see the Loeffler equation as a local description of the curve. And if it's local, well, it should be the same whatever the target is. So what it means is that once we have fixed the time parameter for the radial case, somehow the time parameter for the caudal case should match. And it should tell you that you don't really have a choice here. And you know that it will be written in terms of A, but how it's measured in terms of A, so it has to be linear in A. But you would have the choice of a constant in front, and this constant is determined by saying that the two versions should look like each other. Yes? It's not obvious, but I said it in passing. So what you do is, it's good that I re-say it. If you start from IY, the probability that you touch K is of order 1 over Y. That's by harmonic measure. It's similar to the probability that you touch this interval. And then conditionally that you touch K, the imaginary part is order 1. So let's say it's classical. Okay, so you want to use A of kt as time, but as it turns out, the right way to do that is to assume that A of kt is actually equal to 2t. And you will see in 15 minutes why this 2 parameter comes up. So in other words, gt of z is normalized as z plus 2t of z plus big O of 1 over z squared. So that's the normalization in the caudal case. And as I said before, we are just following the same framework as in the radial case, except that every normalization that comes up is adapted to the topology of the caudal case, so with a mark point at infinity instead of having a mark point inside. Okay, so I'm just coming back for a second to this remark that this parameter A sub A of kt sometimes does not go to plus infinity. So why is that the case? Well, now we have a nice interpretation of A of kt, which is given by this limit here. So if you want to construct a curve that does go to infinity, but for which A does not go to infinity, well, you can just do this. You start from 0, and the curve does something like this. It goes to infinity, but it's following the real line. And it approaches the real line very fast. So this is gamma t. So if the imaginary part of gamma t goes to 0 very quickly, you can take the union of this and fill it, and it will give you this k, which is the inside of the whole curve. So this is k. It's not compact, but I still denote it by k because this will remain true. If this is k, and if you are close enough to the boundary, it's easy to show that this expectation here, this limit, is still finite. Just because if you touch here, it's order 1, and if you touch away from it, then it's of order 0. So essentially what you need is that at distance L, yt is less than 1 over L, something like that, little o of 1 over L. If it's flatter than that, then the tail here will not provide anything into A, and so the A of k will be bounded. So this is something that can happen. It's something that could not happen in the radial case because of the Kuber 1/4 theorem. If you go to 0, then the derivative goes to infinity because it's up to constant the same as 1 over the distance. So this is something that is slightly less smooth in the case of the caudal Loebner chains, that this is possible. But it will be avoided if you just assume that gamma goes to infinity in the nice way. So we assume for now that this is not the case. typically for percolation, it's not the case because of Rousseau-Simon wedge. It tells you that there will be bushes of finite clusters, and gamma will remain above them. So gamma cannot really be flat on the boundary. It has to lift at some point. And when this accumulates, then A goes to plus infinity. Okay. So this was step 1. Step 2 was to derive the Loeffner equation in the radial case. So we'll do the same here. But now this setup is easier to look at because it's easy to figure out what the equation should be. So I look at small t. And I want to go to this, I want to compute d over dt of gt of z at t equal to 0. So I want to compute this. So the first remark is the following. If you take K, which is one of these compact sets, and just to give it a name, this is called typically a hull. So a hull is a relatively compact subset of H, so that the complement is simply connected. So it's something like this. So if A is a hull, there is this map GK, mapping H minus K to H, with the expansion that it behaves like Z plus A of K over Z, plus other terms. So what if you scale K by a positive factor? So take lambda positive and look at lambda K. Can you guess what G sub lambda K is? So G sub lambda K exists, and it's written like Z plus A of lambda K over Z plus higher order terms. But in fact, they are related because if you know how to remove K, you know how to remove lambda K. The way you remove lambda K, so this is K, this is lambda K. I'm drawing it with lambda very small. If you want to map from the complement of this to H, well, what you do is you map to the complement of K by multiplying by 1 over lambda. Then you apply G sub K, and then you see what happens. So if you look at GK of Z over lambda, that's a map that goes from the complement of lambda K to H. So what you get is, well, GK has this expansion, so it looks like Z over lambda plus A of K times lambda over Z plus something. Okay? So this is not G sub lambda K because it doesn't have the right expansion at infinity. It doesn't have the right derivative at infinity as this 1 over lambda. So if you want this expansion, you just look at lambda times GK of Z over lambda, and it turns out that this has the right expansion, so this is G lambda K of Z. So this is the map. If you know GK, you know G lambda K for all positive lambda. And now if you look at the expansion here, what you'll find is that G lambda K of Z behaves like Z plus, so there's an additional factor lambda in front here. So you find lambda squared A of K over Z. Plus higher order terms. Okay, maybe I should write the next term, because that will tell you where the equation comes from. So I will use a different color for that. So G of K will be Z plus A of K over Z plus B over Z squared. So if you look at G of Z over lambda, well, there will be this lambda squared B over Z squared, B over Z squared. And once you multiply by lambda, here you will find lambda cube b over z squared plus higher order terms. So this is just Taylor expansions. It's nothing complicated. It's just matching the parameters. So this tells you two things. It tells you, first of all, that this term in 1 over z should also be a of lambda k over z. So it tells you that a of lambda k is lambda squared times a of k. So this should be something familiar. It tells you that the time you need, so remember a is a time parameter. The time you need to describe lambda k is lambda squared times the time you need to describe k. And this is the same as the scaling you have for Brownian motion. So this is known as Brownian scaling. Somehow it tells you that there is already a link between the Brownian motion or something that scales like lambda squared and the Löwner equation. And if you remember what I said yesterday about Hölder 1/2 driving functions, that's still the same. It tells you that Hölder 1/2 is natural because it tells you that in time lambda squared you vary by lambda. So this Hölder 1/2 is really embedded inside the equation itself. Okay, what else does it tell you? So it tells you that you can write everything in terms of this a of lambda k. K is fixed, and I will let lambda go to 0. So k is fixed. So a of k is order 1 because it's fixed, and lambda up to constants, that's just the same as square root of a of lambda k. Of a of lambda k. So I can rewrite this as, so g lambda k of z, that's z plus a of lambda k of z, plus, and then there is a lambda cube. So lambda cube is a of lambda k to the power 3/2 times a constant over z squared, plus additional terms. And now you start to see that if you want to look at the behavior of the function as t goes to 0, a of lambda k will be t. So this will be square root of t, square root of 2t really. And so you can plug it here and see what happens. So I'll let you think for 10 seconds about what happens when I erase this. So I'm writing this for fixed k, but in fact, this is uniform. If you look at the set of all compact sets of a fixed diameter, then this parameter b is actually bounded. You can compute it by the Cauchy integral, for instance. And what you get is that as long as k is not too large, so as long say that as k is diameter 1, b is bounded by some universal constant. So this expansion, like a to the power 3/2, this is something uniform in the shapes of what you remove from the domain. So if I rewrite this in terms of t, what I have is that gt of z can be written in the same expansion. We know the term in 1 over z because this term is defined to be 2t over z. And we know that the terms of higher order, they will be of the same order as t to the 3/2 or something. And then higher degrees here. You can check that if you continue the expansion, the term over 1 over z to the k will be something like a to the k over 2 plus something, k over 2 plus 1/2, I guess. So, and on all these coefficients will be uniform because they can all be computed by the Cauchy formula. So what you get is that uniformly in gamma, what you have is that gt of z, as t goes to 0, this is z plus 2t over z plus, say, t to the 3/2 big O of 1 over z squared plus t squared big O of 1 over z cubed plus etc. So this is what you get from the scaling. All the additional terms scale with additional degrees. And so what you get is that if you look at gt of z minus z divided by t, well, the z here is here. Here you will have 2t over z divided by t. So that's 2 over z. And then everything else will be of smaller order than t to the power 1/2. So press big O of t to the power 1/2. So what you get in the end is that as t goes to 0, this converges to 2 over z. And what it tells you is that dt of gt of z at t equal to 0 is equal to 2 over z. So this, for the radial case, was a black box. That's where you found z times 1 plus z over 1 minus z. Here it's much easier to understand. You just expand the map and compute explicitly, and you see that you always find 2 over z. So just one remark: if you get the parameterization wrong, and if instead of 2t over z you put some function a of t over z, then the computation still works. You cannot write it as t, but you can still write it as a. And so what you get is, instead of 2, you get a prime of 0. But this 2 over z is always the same. And if you look at the picture, the vector field that is 2 over z is flowing like it did for the radial case. So it's flowing down across 0, and then it splits at 0 and moves to infinity. So if you remark that in the radial case, the vector field was z times 1 plus z over 1 minus z. In the upper half plane, the field is 2 over z. Here the singularity is at 1, like this. And here the singularity is at 0. So in both cases, the singularity is somewhere on the boundary. And if you look at the coefficient in front of the singularity, it's always a first degree singularity. And here there is this 2, and here there is this 1 plus z times z. But when z goes to 1, this goes to 2. So that's really where the 2 comes from. You want the local behavior of the equation to be the same in both cases. So this 2 is just there to match this 1 plus z here. And that will make what follows a little bit easier. OK, we're almost there. Step 3 was to do something about other times. So remember, we were looking at gt, and we want to compute this at arbitrary times. So let's look at t and t plus s. So let's t and s be positive, and s will go to 0 eventually. So this is the upper half plane, and you have 3 copies of the upper half plane. This is the curve up to time t, and this is the curve up to time t plus s. This is gt. So it's mapping the complement to the upper half plane, and it's opening this curve into 2. So this is beta t. This is mapped to some little thing on top of beta t, which is just the gt of this future here. And this is gt plus s. So gt plus s maps the complement of the whole thing to the upper half plane. And the picture in the end is this. And here we have this map, which is G, T, and T plus S. And what we know is that because of normalizations, G, T, and T plus S is nothing more than GT minus 1 composed with GT plus S. So it's GT plus S composed with GT minus 1. Okay, so if we want to differentiate this in S, again, it's enough to differentiate GT, T plus S in S, and then we'll use the chain rule. So we want to look at D over ds of G, T, and T plus S of Z at S equal to 0. And this will be the same as the differential of GT in T for, well, at T. So if you look at the picture, GT, T plus S is almost the same as G for a small time. So you can almost do this. The only difference is that instead of growing from 0, you grow from beta t. So what you want to do is map the beta t back to 0 and apply what we did here as a computation. So I want to define G tilde T, T plus S, which is whatever G would be if this was at 0 instead of being at beta t. So to get it, you take Z, you add beta t, you apply G, and then you remove beta t to have the nice expansion at infinity. So this is G T, T plus S of Z plus beta t minus beta t. So it's just a change of origin. This is natural to do. And removing beta t is just to ensure that the coefficient of order 0 at infinity is 0, so that we are really in this framework here. So G tilde removes a little thing that is stuck on top of 0. And the capacity of this thing, because it's additive, it's exactly 2s. So this behaves like Z plus 2s over Z plus higher order terms. So you can do exactly the same as for time 0. And what you get is that the s derivative of this at 0, so ds of G T, T plus S tilde of Z at s equal to 0, well, it's the same, it's 2 over Z. Then if you want something about G, you have to do the reverse operation. So write G as G tilde of Z minus beta t. And what it tells you, in the end, is that the time derivative of GT of Z, well, will be not 2 over Z, but what you get when you map it back by removing beta t. So what you get is 2 over GT of Z minus beta t. So here I'm just doing 2 steps in one to make it fit in the board. The s derivative of this, the s derivative of G, T, T plus S at 0 is equal to 2 over Z minus beta t. And then if you compose here, what you find is that you get 2 over GT of Z minus beta t. So this is Loeffner's equation in this caudal setup. So what we have is the same as before. We started with a curve. We got a natural time parameter. And the curve read in this time parameter gives rise to a family of conformal maps, GT. And GT is actually a solution of this differential equation with a driving function beta, which encodes everything about the geometry of the curve. So now, if you want to prove Loeffner's equation in the radial case, so the thing that I used as a black box yesterday, essentially the argument is the same. That you can look at the local behavior and prove that the local behavior of a conformal map that removes something very small from the disk the first parameter is describing the size of what we move, and then the other parameters go uniformly to 0 at a given rate, so they vanish in the limit when you take the derivative in t. So I leave it as an exercise to derive the equation in the radial case, following the same strategy as in the caudal case. Okay, I still have about 20 minutes. So in 20 minutes, I want to get to the definition of SLE. And I will say nothing about the features of SLE and keep that for next week. So to recapitulate once more, we started with a discrete model, and I will keep the caudal case for today. So let's say we start with percolation, and there's this exploration process of percolation. We want to say something about the scaling limit. So what do we expect for the scaling limit? We expect a certain number of properties. So first of all, so let's say that gamma delta is the exploration of percolation. So H intersection with delta t, so in the discretization of the upper half plane by the triangular lattice. But this is just for having something concrete in mind. You can look at any interface that looks like that. So think of a Lupier's random walk if you are more comfortable with it. But I'm writing everything in the caudal case. So we know from Smirnov's theorem that as delta goes to 0, there should be some conformal invariant. What that means is that if you take any domain and you put boundary conditions that are red on one side and white on the other side, and if you explore percolation inside this domain, this should be exactly white. No, it's good. It's kind of an ugly color, but is it different from white? Yeah. So, sorry? It's good? So if you look at the scaling limit in this domain, well, this domain can be mapped back to H, where this is mapped to 0 and this is mapped to infinity. We know that the crossing probabilities are conformally invariant by the proof of Smirnov's theorem. So we expect the curve itself to be conformally invariant. So you expect that if you map this back to the upper half plane, what you see here as the image of this under this conformal map phi should be the same as the scaling limit of the exploration inside this domain. So this is one thing you expect. So this is feature number 1. Feature number 2 is the following. So in the Lupier's random walk case, it was non-trivial. Here it will be easier to derive. It's a domain Markov property. What does it say? It says that if you condition the beginning of the exploration to be something, the future of the exploration should be exploration in whatever remains. That was the statement of the domain Markov property for the Lupier's random walk. Here is why it's obvious for percolation. If you look at the discrete process that explores percolation here, and you stop it at a given time. So remember, this exploration is just looking at the colors of the sites when it meets them, and if they are red, it turns left, if they are white, it turns right. But it doesn't tell you anything about what happens here on the complement. So when you are here, all you know is that whenever you were on this boundary, you turned left. So this is red. This boundary is red. And whenever you were on this left boundary, you turned right. So the left boundary is white. Then it tells you that inside you have some information about the colors of the vertices. but you don't care. There are bubbles on which you know nothing and you don't care either, but in the complement here, so let's say this is gamma after n steps. There is this domain which is h at scale delta after n steps. Inside this, you have no information about the colors of the vertices. So all you have inside here is just side percolation at criticality. It's still a product measure. And you have a boundary condition which is white on one side and red on the other side. And that's exactly the setup you started from. It's one simply connected domain with a Dobrushin boundary condition. So the domain Markov property is not even a property at the discrete level. It's just like a statement of the DLR relation, or like the statement of the Gibbs property. If you condition by the boundary of something, what you see in the complement sees that as a boundary condition instead of a conditioning. So the domain Markov property at the discrete level is something obvious for percolation. It's not completely obvious that it's preserved if you go to the limit, especially what the difficulty is when do you stop exploring. You have to choose some stopping time that is non-trivial. So say the first time you exit a ball or something like that. And this can become very technical. So I will not go into that, but let's say that at the heuristical level, it's natural to expect that as delta goes to 0, this is still true. So what you know is the following. So now let gamma t be the scaling limit of gamma delta t. So gamma delta was the exploration process of the discrete model. Gamma t is the scaling limit, so it's a continuous curve. So what do we have? Take h. We expect this to be a curve. So now it will be red because it's back in the continuous case. This is gamma at time t. And if you stop it at time t, you can look at gt of z. Assume that gamma t is parametrized like we just did by the capacity from infinity, so by this term in a over, or in 2t over z. And gt is normalized as before. So this, the complement of this, will be mapped to the upper half. Gamma t here is mapped to beta t, which is gt of gamma t. And okay, let's say that I will just I'll keep like that. So just one remark here: we do not expect the limit to be a Jordan curve. Because of Rousseau-Seymour-Welch, we know that we'll have plenty of loops and that the curve will touch the boundary many times. But if you look at the proof, we did not use the fact that gamma was a Jordan curve. We used the fact that it was a curve and that the Hull kt was strictly increasing. And that is still the case. So all we wanted to prevent was the curve to go inside its Hull and going out somewhere else. And this, the exploration process cannot do because it's stuck by its past. So the fact that the curve was Jordan was too strong an assumption. And all we did, we can still do for a curve with this kind of topology. It can touch the boundary of its past, but it cannot cross itself. So we know that gt is satisfying Leibniz equation. So this is equal to 2 over gt of z minus beta t. So that is still true. What we know now is that if you look at the future of that, in yellow here, this again can touch the boundary of what was before. It can touch its own boundary. And this is gamma at time t plus s. So this is the scaling limit of percolation inside the complement of the curve up to gamma t by the domain Markov property. So the yellow is the scaling limit of percolation in this domain. by 2. And by 1, if you map it by a conformal map, you get something that is the same as you started from. So if you map it by GT, and GT is a conformal map, then this yellow curve is mapped to something like this. And you expect that this yellow picture, which is GT of gamma between t and t plus s, this should be the scaling limit of percolation in the upper half plane. So it should look very much like what you started from. It should look like gamma. So the only difference is that instead of starting from 0, you start from beta t. So this should look, if there is indeed conformal invariance and the domain Markov property, it should look like gamma between 0 and s. The time parameter again is given by the chain rule, so the time parameter is the right one, but with a shift by beta t. In other words, if you look instead of GT at GT minus beta t, you expect GT of gamma between t and t plus s minus beta t to be distributed the same as gamma between 0 and s. So this is the key remark that Schramm did when looking at loop-erased random walks. Assuming these two features for the scaling limit, you get something like independent increments at the level of conformal maps. Something saying that what the map does after time t is the same as what it did after time 0 up to this shift by beta t. Okay, and as it turns out, this will be enough to characterize what can possibly come out as a scaling limit. So let me restate this in a different way, saying that this curve gamma plus beta t, this curve g of gamma minus beta t looks the same as what you started from, can be written in terms of conformal maps. What it tells you is the following, that the map that removes this curve here, we have a name for it, it's GTT plus S. So that's GTT plus S that removes this to the upper half plane. So the map that removes the curve shifted by beta t, so the map that maps the curve which is GT of gamma between t and t plus s minus beta t, that maps this to h. Well, it can be written in terms of GTT plus s. It's GTT plus s of z plus beta t minus beta t. This is the same as before. We just want to remove as much information from the past as possible. Here, looking at GT removes everything about the shape of what you remove, except the location of the tip. And this is encoded in beta t. And now you move this back to 0 by this shift here. And this tells you that you have forgotten everything about the past. So this is removing something that should be like the exploration process of percolation in the upper half plane from 0. So this should have the same distribution as G sub S, because it's removing the exploration of percolation for time S from the upper half plane if you start from 0. So this is what you get from the domain Markov property and from conformal invariance, that this map should have the same distribution as GS. Now, because of what I just said, that you have forgotten all the information, you don't have any information about what the exploration did inside this hull. And because you shift back by beta t, you have no information about where it ended on the R. So you also expect this to be independent from gt, or from g, let's say, gu for u less than t. So you have forgotten everything you did before time t by flattening what you did at time t and then shifting back to 0. So what you did is essentially obtain some kind of Markov property for the conformal maps from the Markov property in terms of the domain. So this is what you get. And now all we need to do is differentiate this in S. So we write gt plus s of z. So what is it? We have this composition. So gt plus s is gtt plus s of gt of z. Okay, and now we will differentiate this in S. And we have two ways of writing it. That will give us a relation satisfied by the driving functions. So if you differentiate this in S on the left, we have Löwen's equation. This is equal to 2 over gt plus s of z minus beta t plus s. So I go from here to here by taking d over ds. Okay, and here d over ds of this guy, well, what was it? This guy is still like a Löwen chain, so it's 2 over something like gt t plus s of gt of z minus the driving function of this guy. So it's beta of the driving function starting from t at time s. So don't look too closely at this notation. It's just saying that this as a function of s is a Löwen chain starting from beta t. So it satisfies the Löwen equation with a certain driving function here. And so you can have this differential here. But now, if we assume that this is true, it tells us that gtt plus s is behaving like gs. So this driving function here should look the same as beta s itself. The only difference is that there's this shift here. So you should recenter it at beta t. And what it tells you is that what will come out once you expand here and once you use this shift is that in the end you will get 2 over, so that's g, so this plus this, so it's the same. You will find gt plus s of z minus beta s minus beta t. And that's an equality in distribution. So this beta s here is the same in distribution as the driving function of this chain here, and it comes from this equality in distribution. And the beta t here comes from the shift that you need here to recenter at 0. Okay, maybe I'm not explaining this right, but that's the idea. You should say that something looks like the initial process. So there is a beta s here, but you have to shift it back by beta t. And so there's also a beta t as a shift here. So nevertheless, once you obtain this, what you get is that beta at time t plus s has the same distribution as beta t plus beta s. Okay, so if you step back a little bit, we started from a random curve here in the upper half plane. But for a fixed realization of this random curve, we have the encoding of the curve as a Löwen chain, so we get this driving function here, which is a function of t. Now, of course, this function is random because the curve here is random. So this random exploration curve can be encoded as a random process. So beta t is a random process. And what we get here is the fact that the random process here has stationary increments and independent increments. In fact, this plus the independent here tells you that beta t plus s, let me restate this in a more, let's say, more French way. Beta t plus s minus beta t has the same distribution and is independent from, well, has the same distribution as the beta s. So it's actually an independent copy of beta s. So this beta t s is an independent copy of beta s. So what you get is that the process beta t has independent increments, because this is independent of this, and the increments are stationary because this has the same distribution as beta from 0. And the last thing is that beta is continuous because it's the driving function of a continuous curve. So what you end up with is that beta t is a continuous process with stationary and independent increments. So what you get from the general theory of processes is that beta t is essentially real valued Brownian motion with a drift. So beta t is equal to at plus, let's say, square root of kappa bt, where bt is Brownian motion in the real line. So that's the only thing that can come up as a continuous process with independent stationary increments. So we are almost there. All we need to do is to rule out the drift term. So essentially there are two ways of ruling out the drift term. And which one you prefer, it depends on whether you like processes or whether you like statistical mechanics more. So one way to rule it out is to say that, let's say we started from percolation. The exploration of percolation is completely symmetric. That the picture is symmetric. If you do a reflection and then you switch the colors, you get the same process with the same boundary conditions, but you swap the exploration process. So the process and its reflection across IR have the same distribution. But it's not difficult to see that if you do this reflection, all you do in terms of the Loeffner equation is to replace beta by minus beta. So what you get is that by symmetry, you get that beta t has the same distribution as minus beta t. And so it tells you that A is equal to 0. The other thing that can rule out the presence of AT here is Brownian scaling. I told you that the Loeffner equation had to do with Brownian scaling. And here we are looking at a curve which is a continuous curve, but it's a scaling limit of something discrete. And if you look at the scaling limit, this is automatically scale invariant. If the scaling limit exists at all, then because it's defined as the limits of a scaling, but nothing can change if you scale a little bit quicker or a little bit slower. So scale invariance of gamma tells you that if you take gamma t and if you look at the scaled version, so lambda gamma parameterized in the right way, but the right way is exactly given by the Brownian scaling of the Loeffner equation. It's the fact that the capacity of lambda k was lambda squared times the capacity of k. So if you want to scale by lambda, you need to look at time t over lambda squared. These have the same distribution. So same distribution as compact sets is because it's a scaling limit, and as parameterized curves is because you can compute the capacity of a scaled compact by Bronnen scaling. So this one has a driving function which is beta t, and this one has a driving function which is exactly lambda beta at time t over lambda squared. And you get that just by looking at the differential equation. What you get is that these have the same distribution. And so this tells you that A is equal to 0, and it fits what you see as B. So that's two ways of saying that the scaling limit has to be driven by square root of kappa times bt. You get a little bit more by looking at the second argument. So if I still have 2 minutes, I started 2 minutes late, so maybe I can use 2 minutes, 5. So the next step would be to say that, okay, we ruled out the drift term. How about ruling out the square root of kappa and saying that, anyway, if you look at Bronnen motion, the square root of kappa doesn't change much of what you see. You can have the intuition that scaling bt here, so changing kappa, will just do a scaling on the picture, and it will vanish in the scaling limit, and it's just a question of normalization. So this is not the case. As you can see here, if you look at the curve and you scale it, what you do is apply Bronnen scaling on the driving function. But of course, this does not change the value of square root of kappa. So changing kappa really does something more than just scaling the picture inside the upper half plane. It really gives a non-trivial deformation. So square root of kappa is a relevant parameter. This gives us the right definition. So SLE for Schramm-Loeffner evolution is the solution of equation L, and SLE with parameter kappa is the solution of equation L with the driving function beta t equal to square root of kappa times bt. So this is where we arrived. So let me restate the theorem that was the whole point of this. If you start with any discrete model for which you have a scaling limit, and if the scaling limit has conformal invariance and the domain Markov property, then there is a parameter kappa positive such that the scaling limit can be described by the Loeffner equation with a driving function which is square root of kappa times bt. So that's the main theorem by Schramm. It's the fact that any conformal invariant scaling limit has to be an SLE for some given parameter of kappa. So next week, I will tell you how to go from this definition and obtain properties of the curves, etc., and then how to identify the parameter kappa from different discrete models. So, well, that's quite a lot of work to do, but I wanted to arrive at this definition to say that, okay, now we have a one-parameter family of random models, and if we know everything about this, probably we learn a lot about discrete models. Okay, so we continue next week, and Vedas has something to say.
my suggestion would be we could start one lecture at 5 until 6:30, and then second lecture from 7 to 8:30. That's proposal, but still I give full decision for lecturers, so they have to be happy, and we need to get okay from support. But from you, are you approving or not? Okay. Okay, so I will tell you decision in the afternoon. Okay, thank you.